Hi, welcome back to College Algebra. We're in section 4.6, and here we're going to look at exponential growth and decay models. So the basic exponential growth or decay model can be given as n of t is equal to n sub 0 e to the kt. And so we're going to go through what all these pieces are in this model, but a couple of things here first. N of t is a function, so this is function notation. Yeah, and I guess that's a good place to start. But also, there are other ways to try and set up exponential growth and decay models, but this will work for really basically anything. And so we're going to basically stick with this model for all of the exponential growth and decay that we're going to do. But let's take a look at what these pieces actually are. So n sub 0 is the initial amount. Okay, so if you have a city, it's the initial population. If you have a culture of bacteria, it's going to be the initial bacteria population. That's a pretty frequent and common occurrence in science. You'll see sub-0 as an initial whatever it might be. In this case, it's the initial number. T is time. Time can be measured in any units, but be careful and pay attention to what those units are. It's going to change depending on what kind of population you're talking about. K is what's called a growth rate constant. This is actually going to be where we have to start all of our problems. We'll be finding K. If K is greater than 0, you have exponential growth. If K is negative, so less than 0, you have exponential decay. And finally, again, n of t is the number, so it's the population maybe after t units, and it is a function. Okay, so this n of t is a function. It's the output when you plug in t. And so we're going to look at a couple of examples, and yeah, it'll be fun. Here we go. Okay, here's our first example. We have a city. In 1990, its population was 100,000 people, and by 2020, its population was 150,000 people. So, we need to, first I have to make a correction over here, but anyway. So what we're going to do is we're going to plug in some numbers into this. We need to find our model. So we know our model is going to have function notation. There's my n of t. My n sub 0 is that initial population, 100,000. And so what I really need is to find k. Okay, if I can find k, then when I put it in that blank up there, we will have our growth model. And then it's something that we can use. So the thing I'm going to notice is that t for this needs to be 30 years. Because we're going from 1990 to 2020, so t should be 30, and sadly, when I did this initially, I put 20, very strangely. So anyway, so I plug in 30 for t, and I'm going to plug in the corresponding number of people that we have after 30 years. I know that if I put in 30, this is the number of people that we will have, so I can put that in place of the n of t, and now solve for k. So I divided both sides by 100,000 because I need to get this exponential piece by itself. That gives me 1.5 is equal to e to the 30k. At this point, I switched it to logarithmic form. I chose base e because that's the base I already have. So I went to logarithmic form. And once we have that, now we have that k with just that 30, and we can divide by 30, and we get that when we type all that into our calculator, the natural log of 1.5 divided by 30, we get the k is 0.02. And so all I'm going to do now is I'm going to come up here, and I'm going to fill in that blank. And this, then, is my growth model. So again, what did I do? I took the initial population and put it in for n sub 0. And then we wanted to find k, so we plugged in 30 for t, because that was the number of years from 1990 to 2020. We put the 150,000 population over here for n of t, because that's the population after 30 years, and then we solved to find k. So I want to do one more part to this problem, but I'm going to have to clear off, about from here down, and we'll work with it there. All right, so here we go. Okay, so now for part B, I want to take my model and find the population in 2050. So in the year 2050, t is going to be 60, because again, our initial year is 1990, and that's 60 years. You can subtract to find that. So I plug in 60 for t. So I'm finding n of 60, right? This is my function notation again. So I multiply up here, 0.02 times 60 is 1.2. Then I follow the order of operations, I do the exponent and multiply by 100,000, and you end up with 332,012. There were decimal places here, but these are people. Doesn't make a whole lot of sense to have a bunch of decimal places, so, round it appropriately. All right, so there we go. We're going to look at another one here next. Okay, so our next example is a half-life problem. The half-life of something is the amount of time it takes for half of the material to decay into another more stable form. If you want more information about that sort of stuff, you're going to have to find a chemist or a physicist or somebody else. I can do the math, so that's what we're going to do. So for carbon-14, the half-life is 5,730 years. I want an exponential decay model this time. It says find a model, but it's going to be a decay model. I didn't give us a lot. All I gave us was the half-life. And so we're going to have to think about this just a little bit, but it's actually going to work just fine. So here's what I have. I want this model. N of t is equal to n sub 0 e to the, and you can see I already filled in k. It's going to end up being negative 0.00012. But that's what we're going to try to find. T. So here's the thing. I didn't give us an initial amount of carbon-14. But it doesn't matter. Because here's what we know. After 5,730 years, whatever we started with, half of it is left. So if I start with some random initial amount, n sub 0, after 5,730 years, half of n sub 0 is left. So I can always set this up using that fraction. This could be with percents. You could have 70% left, and then it would be 0.7 times n sub 0. But so we don't have to have the starting amount here to figure out what k is going to be. So I divide both sides by n sub 0. That gets me to 1/2 e to the 5,730k. I switch it to logarithmic form. So I'm going to use natural log. So the natural log of a half is equal to my exponent. Then I divide. And when I divide, I get that negative 0.00012. And that's my k value. It is negative, which tells us it is exponential decay. But we should probably expect that. This is a radioactive isotope that is decaying into a different form. So we're not getting more of it, we're getting less. And that is what exponential decay is. So there's a half-life problem, and there are lots of other things you can do with it, but that's kind of the basics, and that's generally where you're going to have to start with these. So let's see, I have one more thing left, and it will be fun. So let's get a new board. Okay, so the last thing I want to talk about in this section is something called logistic growth. Logistic growth is kind of exponential growth, but it's exponential growth when there's a limit to how big something can actually grow. So I'm making these videos here right in the middle of the COVID-19 pandemic, and COVID-19 is a really unfortunate, I guess, example of logistic growth. Okay, at the beginning of the crisis, we saw this. If you've looked at any of the maps or the curves that they have drawn of the number of cases, at the beginning of the crisis, it really looks like an exponential curve. But what we get out of it is that there's a limit to how many people can actually get COVID-19. Now, that limit might be every single person in the world, but that's still a limit. Okay, you can't have more COVID-19 cases than you have people in the world. That wouldn't make a whole lot of sense. And so we end up with a graph, and it's going to look something kind of like this. It's going to start really flat, and it's going to curve up like an exponential function would. But then instead of continuing up forever, it's going to level out. And it levels out at what we call the carrying capacity, C. And so you end up with this sort of curve, and if you can find a graph of the total number of COVID-19 cases, it's going to, over time, look more and more like this. Now, it's a nasty formula. P of t is equal to c over 1 plus a times e to the negative bt, where c is their carrying capacity, b, which is actually a number bigger than 0, is the growth rate constant, and a has its own little formula, c minus p sub 0 over p sub 0, where p sub 0 is the initial. In the case of COVID-19, it would be the initial number of cases. Now, this one's big, it's kind of messy, it's complicated. You'll probably see a couple of examples in your homework. I will tell you that I'm not going to put this on your test, but it is something that is interesting, and it's certainly quite topical right now. So anyway, this is logistic growth. There are lots of examples out in the world of where logistic growth comes into play. But COVID-19 is one that we certainly have in front of us right now. So anyway, that's logistic growth. And that is exponential growth and decay. Have a great day.